few moments before to enable some questions and answers to be given. We start with the first communication on optical wavefront shaping and extension of small particles, clusters, and 3D finite samples. I will chair the session. I'm Adrian Podoleanu, University of Kent, Canterbury, UK. The presenter will be Willem Vos. They are from Complex Photonic Systems, MESA Institute, University of Twente, Nanophotonics, Dubai Institute of Nanomaterial Sciences, Utrecht, and Institut Langevin in Paris.
Thank you very much, Professor Podoleanu, for kindly chairing the session and for the kind introduction. So, good afternoon, dear colleagues, friends. My name is Willem Vos, and it's a pleasure to present this talk on behalf of Ad Lagendijk, the first author, and Allard Mosk, the second author. And indeed, we're from Complex Photonic Systems in Twente, and Allard used to be at COPS and now is at the Dubai Institute in Utrecht. So I'll tell you about optical wavefront shaping and extinction on small particles, clusters, and 3D finite samples. In this cartoon, I will explain a little bit later. Okay, of course I would also like to thank many COPs who are listed here. I will not name them for the sake of time, and also colleagues within the Netherlands and colleagues all over the world with whom we collaborate, and of course our funding agencies. Okay, so what is the take-home message of this presentation is that usually we do light scattering and optical wavefront shaping on samples with infinite support. So think of a typical proverbial slab on which we send a wave from a laser, and this may be shaped. That's why there's this interesting structure here of the light modulator, and then you succeed, you say, hoo-ha, I've managed to shape this into a very bright spectral spot. However, see, the sample is much greater than laser beam. That's why we call it quasi-infinite. However, in all the applications that we meet from our friends in industry, the samples are always really finite, and this can vary from climate, and I repeat, climate, because we should spend much more effort into dealing with the climate crisis, biomedical, high-tech, etc., etc. So the samples are finite, and okay, this is not dealt with in the usual descriptions. So this is why today I would like to give you some idea of the theory and analytic calculations that we have started up and do for scattering and wavefront shaping on samples with finite support. And of course I forgot to say that this is Ivo Velikoop and Allard Mosk, again Allard, because they're the inventors from a group who invented wavefront shaping in this legendary paper. Okay, so here is a scattering sample of whatever shape and filled with whatever scatters it might want to be. And so let me briefly discuss this issue of finite support. So it means that the sample is sitting in an environment which has open boundaries. So there's a wave coming from somewhere, not out of magic, but out of a well-defined source. And then the waves are going forward. You get extinguished waves, so extinction. And there's of course waves which are scattered in all directions. And these waves are going anywhere. Let's say from Munich, where we are, they might go up into space, they might go to Austria, they might go to Switzerland, to Britain and the Netherlands. And what I mean by extinction is of course the removal of energy from the incidence of what we see at the back. And this is from the combination of effects that are happening in our sample, which are a combination of scattering and absorption. I should press just one button. If it still works, yes. So usually in light scattering we study slabs. So here I've expressly covered the whole slide to make clear that the slide has a finite thickness, but the extent laterally is typically quasi-infinite, and of course also coming forward into the room here. So that means that this sample has infinite support, as we say. So typically when we do an experiment, we shine light on this, and we might even wavefront shape, again to get a bright spot at the exit. We typically might like to in fact use random matrix theory, which is very popular. We've also used it. Or you consider your sample to basically be a waveguide, which is a bit awkward given that your sample is really scattering. But it works beautifully, and you can use it, but yeah, still, there's limitation to it that we will overcome. So in this scattering picture, we say that the total wave function, so this is not necessarily quantum mechanical at all, this is in fact a classical wave, typically this is the E field, H field if you like, equals the sum of the incident wave that you send in from your laser, light modulator, which is going to the sample, and then the light is scattered, so there's a scattered wave, and both of them total give you the total wave. Now the consequence of a scattering slab with infinite support is of course that at the back of the sample where you typically do your wavefront shape experiment, there's no more psi in, there's no more instant wave because it's completely scattered by these objects in here. So in the infinite support sample there is no more psi in, and so therefore conversely in the finite support sample, like this finite block, there's always infinite wave. Here's a side remark from my physics lawyer. So we're really interested in strongly scattering samples, and not really in window panes. Although with our theory later on, we can also deal with window panes if that's needed. So what I mean by extinction technically is that if you have an object which is now finite, and you send in waves from a source, brainwaves maybe, then these waves go forward because they extend, let's say the planes extend very far. And then on your detector, you look in the direction of where the waves come from, and you see the interference of this instant wave with the waves which are scattered by the object, and the forward scattered waves interfere with this instant wave, and this gives you the shadow, like the shadow on this beautiful block here. And shadow is of course what we direly needed in Munich all week when it was really sunny and hot. We were looking for shadow. For trees, and the trees are basically phase shifters. We phase shift the instant wave to become extinct, and then it's nicely dark and cool. Okay, joking aside, so this interference in the forward direction is extinction. And extinction, and there's a formula which we'll skip, extinction does not exist, again, for samples with infinite support. So slabs, waveguides, infinite crystal. And that's of course because the instant waves are absent. So briefly, which is also popular, is to consider a waveguide which is filled with scattering material. You send light on this side, and this could also be a fiber, multimode fiber with disorder, and you look in the exit, again at wavefront shaping. But again, at the exit of this multimode waveguide with disorder, there is no incident field anymore, so again, you do not have extinction. And of course, I know very well that the area of this fiber is finite, but yeah, it's a good fiber, so that means that the field we sent in does not extend outside. It's only inside the fiber here and not outside, so therefore it's again quasi-much infinite support. So the theory that we set up, I'm not going to show you equations because it's Friday afternoon after a long week of conference and exhibit. So what we use is we started with the scalar wave theory. Yes, apologize, we're opticians and we should eventually extend it to vector waves. But I can tell you later on why it's already a pretty good start. And we can compute the scattering properties exactly. So here I have an example of a box of 4 by 4 by 4 wavelength cube, which is filled with 1,000 dipoles. Okay, these dipoles are points, and if we would draw them, you would see nothing because the points are empty. However, since these dipoles are in their resonance, they have a polarizability. So these spheres here, which look like blueberries, are basically the polarizability. It's the property that the light sees whenever it would enter here. So we can vary sample shape, we can fill in up to 20,000 dipoles, because we have a very modest computer, otherwise you would even more. And in this case, the polarizability is so much that the mean free path, scattering mean free path over the wavelength is 2/10, so 20%, or if I would normalize the scattering mean free path over sample size, it's about 5%, so it's really a opaque sample. Our sample in our calculation is, again, a block is here, if you like, and now we send in waves with different phases because we want the wavefront shape. And of course, theoretically, you can invent any phase, 1, 2, 3, 4, 5 with 5, or how many beams you want. You can look in forward scattering, and you can look in all the directions that you want to go. So we sent in waves from m different directions, which we can take care of to be at least 400. So this is effectively like having 400 pixels on our SLS by nearly 60%. And recently we've also done experiments in a similar setting where we took a silicon bar where we sent in just 2 beams, we shaped one beam to the other, and then we see that the extinction is angle dependent beam, and we can make the extinction twice as big, so the bar becomes twice as dark, or it can become really bright, meaning that the bar is basically transparent. In the meantime, we've done experiments with 64 beams, which is a lot harder, and we still have to get around to write the paper. So to summarize, we've devised a theory for wavefront shaping the assembles with finite sports, particles, clusters, finite, you name it. And we conclude the scattering property exactly by basically using n resonant dipoles. So we can use wavefront shaping on the typical target of one outgoing direction, a spectral spot, traditional one, and we can also control extinction or the shadow of the sample. So applications would be, for instance, sensing a particle displacement inside a completely opaque medium, which maybe is useful for biomedical or semiconductor applications. So this is the step towards the direction that we want to really solve scattering, what problems we can address, maybe understanding propagation and scattering, maximizing, minimizing absorption, maximizing scattering if you want to have white LED, maximizing extinction or minimizing if you want to hide or look through and control directionality. And with this, I'd like to thank you for your attention.
Okay. Thanks. Any questions? I know that we don't have too much time because we have to move to another. I think the subject would have deserved more than 15 minutes, but I have a comment. Somebody said that instead of other theories trying to maximize the peak, you are practically trying to reduce the, let's say, the values. Is that a misinterpretation of your theory?
Okay, sorry if I was too fast anyway. See, but with our theory, you can do whatever you want. So you can say, okay, I choose a beam in a certain direction. Can I enhance this? Yes, you can. Then you have to set the phasors, which you can do. If you say, okay, can I do it less? So can I make it darker? Then that's certainly that's feasible. It's completely feasible.
And you also insist on phase, but
yes.
you have